Back to the last day of talks. So it's my great pleasure to introduce Eyll from Bochum, and he's going to talk to us about the stability of systolic inequalities for the Klein bottle.
Yes.
Thank you, Jan. And by the way, thank you for accepting giving a talk in short notice.
Yeah. So thanks to the organizers for this very nice conference and for the quite spontaneous opportunity to talk here. So let's just jump right in. So for a closed surface M, which is for me today not a sphere, so M not S2, and for Riemannian metric on it. I will denote with alpha cis of M G the systolic area of M. So the area divided by the square of the systole. And for me, the systole is the length of the shortest non-contractible closed curve, so the homotopical systole. And where this notion was basically studied quite some time ago already. So I believe in the late 40s, Löwner made the first discovery basically in the field of systolic geometry, where he showed that on the torus, the systolic area on the two torus for any metric is always greater than the square root of 3 over 2. So this holds for all metrics on the torus, and we also know that equality is only attained if the torus is isometric to an equilateral flat torus. And also a bit later, Pu discovered a similar result on the projective plane. So he showed that the systolic area on RP2 is bounded from below by 2 over pi. And basically the next result in this list is on the Klein bottle. So in the 80s, Bavard showed that on the Klein bottle we have that the systolic area is always strictly bigger than 2 square root 2 over pi. This is a strict inequality if we consider only smooth metrics, but if we allow singular metrics, then we also know the up to rescaling unique minimizer of this systolic area. And basically this inequality and the stability of it will be what I want to talk about today. And so when you work on surfaces, it's always useful to use conformal metrics and conformal classes, because the conformal representation theorem gives us that on a surface any metric can be written as a conformal factor times a metric of constant curvature. So on a surface, any metric is of the form so some conformal factor, some function, times metric G or G0, where G0 has constant curvature. And if you know the proofs of any of these results, this is heavily used, and basically the main argument or the main point of the proof, or a key point of the proof. So if we want to look at the Klein bottle, it's useful to understand the structure of the space of conformal classes. So we denote with CK the space of conformal classes. Of metrics on G on K. And so by the conformal representation theorem, we know that well, every conformal class has some metric of constant curvature. And of course, on the Klein bottle, constant curvature can only be achieved by flat metrics. And one can actually show that this space can be parameterized by the interval 0 to infinity, so by positive numbers, where to some beta we assign the conformal class C beta, which is the conformal class of a specific flat metric, so which I will denote with G flat beta. And this will be the metric defined in the following way. So we take a rectangle in the plane, and the side length are, so this side is of length pi, and this side will be of length 4 times beta. It will be clear later why I choose the normalization of 4 beta here. And then we identify the sides in this way to obtain a Klein bottle. And the metric which we get from the standard metric on R2 under this identification is, this will be the metric G beta flat. And this Klein bottle I denote with K beta. And so Bavard not only showed this inequality, but he also had conformal inequalities. So in the 80s also, he showed that for any positive beta, there exists a constant some number A beta, such that the systolic area of K and G is always greater than or equal to A beta, and this systolic inequality holds for all metrics in this conformal class C beta. So for all G in C beta. And this constant A beta, this is known, so there are formulas, you can just write it down explicitly. And furthermore, we also know in every conformal class some conformal factor for which this inequality is an equality, so this is a sharp inequality. But the point is, or the thing is that maybe these conformal factors are not smooth functions. So if we allow non-smooth conformal factors, this inequality is sharp or can also be achieved. And the explicit minimizers are something which we will also see, if I have time, some of the constructions today. And it's also quite interesting to look at the graph of this function beta maps to A beta. So for small beta, it looks like it's proportional to 1 over beta. Then it has some more complex behavior, and then after some value it grows linearly. And this unique minimizer is what we call beta 0, and of course the minimal value is the 2 square root 2 over pi, which we saw already. And so this conformal inequality is the inequality which we will study today. And so I can now present the theorem. So for any beta positive and for metric G of the form f squared times G flat beta, we know that if we take the difference of the function f minus a function p beta of f, this p beta I will explain in a second. If we take the L2 norm of this, and so f and p beta of f will be functions on K, and so the space of L2 or the L2 scalar product will be taken with respect to this flat matrix, so K G flat beta. If we divide this by the square of the systole, then this is a lower bound for the difference between the systolic area and this number A beta. So what this basically, so I should say what this P beta is. So where P beta is the orthogonal projection in this space onto the space of a function f beta, which I also haven't explained yet. So this is the L2 for orthogonal projection onto the subspace R times f beta in this space L2. And this function f beta is the up to rescaling unique function such that this inequality is an equality. So and f beta satisfies that the systolic area of K and f beta squared G flat equals A beta. So now if we look at what you have here, this thing of course is always greater than or equal to 0. So as a consequence we get that this systolic area of the metric G is always bounded from below by this number A beta. And furthermore, we know that if we have a metric in this conformal class such that the systolic area is close to the optimal systolic area, then we can say that this conformal factor f has to be close in this L2 sense to the optimal conformal factor. And as a corollary, because we know exactly how this function A beta looks, we also get a similar stability result for this original inequality, where we basically can say if we have a metric for which the systolic area is close to this, then we know that the value A beta has to be close to 2 square root 2 over pi, and again the conformal factor has to be close in this L2 sense to the optimal conformal factor. So in the remaining time that I have, I will try to motivate and show the construction of this optimal function f beta, and maybe say a few words about the proof in the end. So for the construction of this optimal function f beta, so for now on we work in a fixed conformal class and want to find a function f beta which in this conformal class minimizes the systolic area. So we want to minimize alpha cis f beta squared G flat. And the first thing that you do, which is also what is used in the proof for the inequalities on the torus and on the projective plane, is that when you have such a conformal factor, you can always average over the isometry group of the flat metric, and this will always increase the systole and decrease the area. So in turn, the systolic area will always decrease. So when we do this, we have to take a look at how the isometries of this flat metric look like. So one isometry, or one class of isometries which we have, are the translations in the x direction. So we have isometries of G flat. So the first class of isometries are translations in the x direction. And a second isometry is if we consider this rectangle to be in R2, where this here is the line y equals to 0, then we can reflect at this line, and this gives us an isometry. So we have the reflection at the line y equals to 0. And we can also look at this a bit more carefully. So if we have here the value beta and here 2 beta, minus beta and minus 2 beta, then this region here in between beta and minus beta, this is a Möbius strip. And these regions together here, this outside and this, also combines, if you take this and put it here, is also a Möbius strip. And what we can do, which is an isometry, is we can swap these two isometries, or basically if we combine this with the reflections at y equals to 0, this allows us to reflect at these levels y equals to beta. And what this gives us is that instead of having to work with a function that is defined on all of this Klein bottle, so the first class of isometries allows us to only focus on functions which are defined on this interval 2 beta and 2 beta, because any function which is invariant under these isometries will only depend on the y coordinate. Then if we utilize this reflection at y equals to 0, we can only consider even functions and look at how it behaves on the interval from 0 to 2 beta and continue this by reflection. And the same we can do with reflections at this level beta. So what we are left with is we only have to consider functions which are defined on this interval 0 to beta. And here we will also see why this can introduce non-smooth functions. So if we take something like this as our function f defined on the interval 0 beta, if we reflect this function at this level, maybe we get here some singularities, because if we just, without care, take any function f, there's no need for this reflection to be smooth again. And this is also actually what will happen. So if we want to construct such a function, now let me erase this. We have to look at what does it mean to minimize the systolic area. So basically what we can do is we can we can fix the system of fg to be equal to pi, and then want to minimize the area under this constraint. And a direct calculation shows that the area is proportional to the integral from 0 to beta of f squared. So basically, we want to minimize this square of f under the constraint that the system should be equal to pi. And this constraint gives us some things to work with. So, for example, the first thing which we get, well, because this says that every non-contractible curve has to be of length at least pi. And so we can look at curves that cross the Klein bottle like this. So they go straight down, and this is a closed curve. And so the length of this curve has to be at least pi. And if we calculate this, so this length is equal to the integral of minus 2 beta to beta f of y dy. This is supposed to be bigger than pi. So using the invariance properties of f, we can just integrate from 0 to beta and get the constraint that this integral has to be bigger than pi over 4. So this is constraint number 1. Another thing which we can do is we can look at curves that start at any value of y. They just start here, go straight to the other side. Then we will come out here and go also straight in this direction. So this is a closed non-contractible curve. And if we calculate the length of it, so the length of this curve, if we start at some level y, is precisely equal to 2 pi times the value of f at this level. And so this needs to be bigger than pi, so we get the second constraint that the function f always needs to be at least 1/2. And a third class of curves which we have to consider are the curves that start here and without crossing, by just crossing once, go through this point on the other side. And if we look at what we have, this is now basically a curve in this embedded Möbius strip. So in the paper from Pu, where he worked on the systolic inequality on the projective plane, he also had some results about the systolic inequalities for conformal classes of metrics on the Möbius strip, and this is precisely what we need here. And if you look at it carefully, you get there that if the length of all these curves is bigger than or equal to pi, then this gives us some constraint that for all z between 0 and beta, we have that f times phi 0 has to be bigger than the integral 0 z of some function phi 0 squared, where phi 0 is a specific known function, so phi 0 of y is e to the y over 1 plus e to the 2y. And this is basically the conformal factor which you get when you take a Möbius strip embedded in the sphere and pull it back to such a rectangle. So this is the third constraint. And under these constraints, we want to minimize this integral. And I don't have time to show the complete construction of f, but maybe just one example, because depending on the value of beta, these constraints are so they have to be balanced with each other. So for small values of beta, this is not so easy to achieve. And so this is more dominant, and for larger values of beta, the other constraints are more important. So for example, if we take beta between pi over 4 and this minimizing value beta 0, then, so basically the idea is what you would like to do is you would always want to use the function phi 0, so you don't have to worry about these curves in the Möbius strip. And the graph of this function phi 0 looks somewhat like this. And if we have the value beta 0 here and some value beta below it, then this value beta 0 is precisely the value for which the integral of beta 0 of phi 0 dy equals pi over 4. So if we are below this value and just take the function phi 0, then this first constraint will not be satisfied. So what we will have to do is, or what we can do is, well, there is some value s beta below beta, so that if we continue our function, so up until this point we use phi 0, and from this point on we just go constant. And if we choose this value s beta correctly, such that this total area is equal to pi over 4, then this is what is the definition of the function f beta in this case. So f beta will be equal to phi 0 of y for y less than or equal to s beta, and just phi 0 of s beta for y bigger than s beta. And again, this function is only continuous and not smooth at this point. So, and now I have like 3 minutes left to talk about the idea of the proof. So the proof, as mentioned before, basically step 0 would be to use averaging over the isometries. So if we have this, then what follows directly from a calculation is that if we look at the area of some metric f times g flat, this area is basically just the L2 norm of this function f. So this just gives us, or we can write this as the area of this projected metric and we also know precisely the amount of area that we lose, which is this difference, the L2 norm of this. So basically, because of this, we have complete control over the area, so we know what happens precisely when we project. And this is what survives in the end, this difference of the conformal factors. And so basically, what we have to show it is that this projection does not decrease the system. So we want to show that the projected system is always bigger than or equal to the system we started with. And basically what we do for that is we look at the formula of this projection. So f is equal to the scalar product of f with f beta normalized, and then times the function f beta. And so what I claim is that if we start with a function f such that the system is equal to pi, then this constant in the projection will be bigger than or equal to 1. And this will mean that the system will not decrease. So the claim is that if the system of f squared g is bigger than or equal to pi, then this scalar product f with f beta is always bigger than or equal to the scalar product of f beta with f beta, and something which I didn't mention already, but which is basically also part of the construction. And we know that the system of f beta squared g flat is always equal to pi. This is basically by construction and by rescaling. And so if we combine these results, if we start with a metric with system bigger than or equal to pi, then where this constant or this factor is bigger than or equal to 1. And then our conformal factor after projection will be bigger than the optimal conformal factor f beta. And so we get that the system is bigger than this. And if we put these two inequalities together, we get precisely the result which we wanted to get. So yes, I think this will be all.